So this talk is special. Every talk was special, sorry, okay, this was really undercut in the moment. But I'm really glad to welcome Emanuele to the stage. Emanuele Fabbiani, also known as Lele, he's the head of AI at xtream. Small disclosure, I work for there too. But he will be talking about diffusion models with a really enticing title, Ordo Chaos. So I expect a lot of questions from you too, as well. So without further ado, let's welcome Emanuele to the stage.
Good morning, everyone. Today we are talking about diffusion models. I guess everyone in this audience has played with DALL-E or with Midjourney. And probably you have seen something like this.
Oh dear Lord! That's classic!
You spin my head right round when you go down, when you go down, down.
You spin my head right around when you go down, when you go down.
Walk up the house with my swagger, hop in that window, I got places to go. People to see, time is precious, I look at my Cartier out of control. Just like my mind where I'm going, the women, the shorties know nothing but clothes. No stopping at my Pirelli's on, unlike my jewelry that's always on. You spin my head right round when you go down, when you go down, down.
You spin my head.
And we must understand that this is from the beginning of 2023. So by the pace that innovation is going right now, that's already a little bit old. Midjourney 6 was not there yet, so you can do better now. You can do something like this, for example. This person does not exist. This was generated with Midjourney 6. It looks real, it's pretty impressive, and if you compare this picture with the video that we have seen just a few seconds ago, you can already see the difference in quality, and these two assets were less than 1 year apart. So diffusion models are a real thing. They are already being used in marketing, in campaigns, in creating company assets. But today we're not going to talk only about how to use them. So for sure, we do not need to understand how Midjourney or DALL-E work in order to use them, but knowledge is fun. So for the love of knowledge and of science, in the next 30 minutes, I will try to explain with just a few equations, how diffusion models work, what are the merits, what are the limitations, and how they are likely to change the way our company communicate. Are you ready? Let's start. And with every research that serves some merit, we should start from Wikipedia. This is from the page of Wikipedia talking about diffusion models. We can see that diffusion models are a class of latent variables generative models. They are made of three major components: the forward process, the backward process, and the sampling process. Now, if you understood these two sentences, you can go to the other room, because this talk will add nothing to your knowledge. But if you're curious to understand what stands behind this text, then you're welcome to stay here. We shall start from 10 years ago, it's 2015, and from a different field of science. We shall not start from computer engineering, but we shall start from physics. In 2015, this paper was published. It is considered as the first paper about modern diffusion models. And it's not about pictures, really. It's about deep learning and non-equilibrium thermodynamics. Why? Let's take another step back. And let's talk about a basic concept in physics. Let's talk about entropy. What is entropy? Well, entropy is a state variable of a system that measures its degree of chaos. That's where the title of the talk comes from. Entropy is actually a measure of the disorder of every physical system. So you can see entropy at work here. At the very beginning of this video, the 7 colors are perfectly distinct, so the entropy is relatively low because all the colors are concentrated in one point. As the video progresses, the color diffuse into the fluid and they mix between each other. So the entropy increases as the disorder of the system increases. Now, we have the second law of thermodynamics that tells us that every transformation in a closed system, that is, every transformation in a system that does not exchange energy or matter with the external universe, goes towards an increase in entropy. So this video goes into the right direction. If we were to look this video backwards, we would go against the laws of physics. So going from a more ordered state to a more chaotic state is easy because you can just follow the laws of nature. Going from a more chaotic state to a more ordered state is difficult because you need to go against the laws of nature. Usually you can do that, but you have to pay a price. And the price you have to pay is just to give energy to your system from the outside. Right? Okay. Now, I open and close very quickly a small parenthesis. Entropy is nothing more than statistics. You go from more ordered states to more chaotic states just because more chaotic states are more likely. Imagine to toss a fair coin 1,000 times. It is much, much, much more likely to get about 50% heads and 50% tails than not every toss is a tail. Just because there are many more combinations, many more possible outcomes that go towards the first case than toward the second one. It's the same here. It's much easier for particles that move randomly to diffuse uniformly in the fluid than to stay concentrated just in one point. It's just more likely, nothing more. Good. Now, why this matters to our diffusion models? Well, let's take a more schematic representation of the process. So the video was showing the first part in this slide. So we go from concentrated information from a more ordered state to diffused information, uniform information, so a more chaotic state. If we were to go back in time, we would do this, going from a chaotic state to a more ordered state. Okay, you probably have already connected the point. Diffusion models do this. Ordo of Chao, order from chaos, they reverse the laws of physics. How can they do that? That's next chapter in our story. So now we know the problem. And by the way, we know what the first part of those Wikipedia text means. Forward diffusion process is creating chaos from order. Reversing the diffusion process is creating order from chaos. And that's what we're going to see right here. But let's set a little bit the stage in the computer vision domain. So this is exactly the same as the video of the colors diffusing in the fluid. So we are going from a more ordered state, a real picture that is a real man, it exists, to a more chaotic state that is just random noise. How do you do that? It's easy. You destroy the structure of the picture. How do you destroy the structure of the picture? Adding noise. How do you do that? Well, you start from the initial picture, and then for each pixel, you sample from a Gaussian distribution centered in the real pixel with a certain variance larger than 0. And because it's nice and it makes the math work, you also shrink the average of each pixel at every step. Let's say that t is 1,000, which is pretty realistic. So you have 1,000 steps, where at each step you add some noise to each pixel of the picture. If you made your schedule of adding noise good enough, at the end of the day, you will have something that is indistinguishable from random noise. So you could have started from this with random noise, and it would be exactly the same in terms of probability distribution. Forward diffusion, chaos from order. This is easy. It's just adding random noise. You can do that with 3 lines of code in NumPy or whatever is your favorite library. Very good. It's important, and we will later see why, that this is a Gaussian distribution. Otherwise, that the math that we're going to use in the next slide will not work. Very nice. Oh, there is a little trick here. So the step from 0 to 1, the step from t minus 1 to t, all have a Gaussian distribution from one time instant to the next one. So the process of forward diffusion is just adding Gaussian noise. Gaussian distributions have this very nice property that the sum of Gaussians is again a Gaussian distribution. And this noise is added by you, so you control the distribution, you know the average and the variance, so you know everything about this distribution. So what you can do is just write down the equations and skip from step 0 to step whatever, between 0 and capital T, without computing all the intermediate steps. You can do directly in closed form, and then you can use the formula to just make the computation very efficient. So here you can go from step 0 to whatever step from 0 to capital T easily in big O of 1 time. Very nice. Now that's the difficult part. So you need to inverse the process and reconstruct the original image from random noise. How do you do that? Theoretically, it's easy. You just need another probability distribution. What's the probability distribution that you're going to need? The one from t minus 1 to t. No, sorry, the other way around. So the 1 to t from t to t minus 1. So it's p with parameters theta of t minus 1 conditional on t. What's the bad news? You don't know p. So you have to reconstruct the probability distribution. That's the same problem you have in non-equilibrium thermodynamics. So this is exactly why the first idea of diffusion models came from physics, because this whole idea of reversing entropy, of course, in physics has a lot of application. You can study phenomena in a different way if you know how to reverse the normal execution of processes. Very well. What can we do here? So the problem is very hard. You have to estimate a probability distribution for each step, and you cannot skip steps here. And you have to estimate a full probability distribution, not just 2 parameters of a Gaussian distribution where with average and variance you know everything. But as you chose Gaussian as the distribution to destroy the structure of the image, you have some very nice mathematical result that tells you the distribution P is also Gaussian. Nice. So now you have skipped from the problem. We will go through the details in a moment, but believe me, you have now a much easier problem. You do not have to estimate a full probability distribution. You just have to estimate the average and the variance. Still hard. The variance in particular is a matrix for each pixel in the image. It's very hard. So in the original paper of diffusion model, they say, we don't care. Let's just set the variance at sigma squared times the identity and pray for it. It worked, so great. Why does it work? We don't know, but it worked. So now we have a much easier problem that is estimating only the average, right? Math again comes into play and tells us that an even easier problem is just to estimate the inverse of the noise that you need to go from step t minus 1 to step t, to then derive the transformation that you need to go from step t to step t minus 1. So do not predict the picture as step t, just predict the noise. It's easier, and you can show that the noise is a Gaussian distribution under some assumption that you think you're right. Okay. And now we have come to the final problem. So the final problem is we have to estimate the average of a Gaussian distribution from each step to the previous one. And this is where we throw a huge neural network and we pray for the best. And again, it worked. So this is an example of a neural network that you use to estimate that parameter of the inverse transformation for the probability distribution of the noise. Again, here you are only estimating the average, then you know that is a Gaussian, and you have set the variance, so you have everything about the distribution, you can use it to sample different samples of the images at each step in the backward diffusion process. Okay, how does it work? This network, this was in the first generation of diffusion models. Then we will show a picture from the stable diffusion paper. We will see it's much more complicated nowadays, so let's start from the simple one. What we see here is that we have skip connections, and then we have this U-shaped architecture that gives the name to the network. This is called UNet, because you go to smaller and smaller spaces that are meant to capture the semantic of the picture, and then you basically reconstruct to the full resolution. Very good. So we know what the forward process is now. Forward process is just destroying the structure of a picture by repeatedly adding noise in small steps. We know what the backward diffusion process is. It's just reconstructing the structure of the picture in small steps, and now you have to use small steps because you cannot skip. You do not have that great properties of Gaussians to help you yet, because you do not know how to condition in each step. And now we know also what is the sample procedure, because we estimate the parameters of a probability distribution, but we need to sample from that probability distribution to have the image at each step. So we have basically explained that very nice paragraph from Wikipedia. Now, from here on, the theory is over. We will try to improve from this basic model. The first, well, this is just a graphical representation of the same process. You go from real images to chaos and the other way around. By the way, such a model is pretty easy to train because you have all the data in the world. Because you're creating your own data. You're taking just a huge data set of picture, ImageNet or whatever is the state-of-the-art data set, and you destroy the images for 1,000 steps, and you go all the way round to the original picture. You know what the original picture was, so you can compute the difference, you can compute the loss function of the model. Okay, you can't, because the real loss function of this model is, again, a likelihood computed on probability distributions that are conditional on each step, so it's numerically intractable. What you do is compute a lower bound of that likelihood and maximize the lower bound so that you maximize the likelihood. But, I mean, it's not very important. Now, to the heuristics. First is something that I've already talked about. It's much easier to predict the noise in the reverse diffusion process than to predict the picture. Why? That's why. This is a paper, again, and the first paper we talked about was from 2015. This looks weird. It looks older. It is from 1949. Just to give you an idea, the most important historical event in 1949 was the Soviet Union detonating its first atomic bomb. So we were there with technologies, right? And this feller wrote a paper about the theory of stochastic processes where he showed, like with paper and pencil, that in the backward diffusion process, the difference between one step and the previous one under some mild condition is a Gaussian distribution. So whenever you hear something saying that base research is worth nothing and we should only invest in applied research, then show this example. Very well, second heuristics, predict small steps. Why? Once again, this fellow said that you can assume that the difference between one step and the previous one in the backward diffusion process is Gaussian if the step is small enough. So if the difference between the two images is small enough. That's why you need lots of steps in the forward diffusion and lots of steps in the backward diffusion. And this is why you need to predict in small steps going backward. This is very annoying for engineers because predicting in small steps is very inefficient in a computational point of view. And I mean, when these models become economically profitable, engineers rush to optimize this point, and they did it. Nowadays, diffusion models are able to skip and not do 1,000 iteration in the backward diffusion process, but they just skip like 20 by 20 or 50 by 50 using some clever heuristics. And the third point is you control how you destroy the structure of the pictures, so you shall do it wisely. Doing it wisely means first using Gaussian noise, and we have already discussed why, but second, how much noise do you need to add at each step? Should you use always the same amount? The answer is no, you shan't. Why? I don't know from a theoretical point of view, but empirically, in 2022, it was shown that if you add very little noise for the first, like, 100 step, then you add more noise, and then you add again very little noise for the last 100 steps, the results of the reconstruction are much better. Why? Because, at least empirically, the first and the last steps of the reconstruction are the most difficult. So you want to have very little noise in the first and the last steps of the forward process. This is called variance schedule because you create literally a schedule for the variance of the noise that you add at each step of the forward diffusion process. Now, last chapter in our story, controlling diffusion, because up until now, we have shown how to create pictures literally from nothing but noise. But we do not want just to create pictures. We want to create pictures that look like we write. So we want prompting. How does prompting come in here? Well, first, a little bit of engineering. I didn't tell you the whole truth. Nowadays, modern models, like from Stable Diffusion onwards, do not really perform diffusion on pictures because it's too inefficient. What they do is that they encode pictures in latent spaces, they do forward and backward diffusion in the latent space, and then they decode the image back. Encoding decoding is performed by an autoencoder, so something that compress the picture to a matrix, to a space with lower dimensionality. You can think about a full resolution picture to a, I don't know, 100 by 100 matrix. I'm making numbers up now. And then you convert back, right? The diffusion process works in the latent space because the latent space is smaller, so it's easier to perform all the steps, including the reconstruction. Now, in this paper, 2022, OpenAI, they say, look, let's take an architecture like this one, okay? and compare it with generative adversarial network that were the state of the art for image generation. It's better. Fine. But they also say, if we had a classifier in the system, like the ones that you have seen in the last two talks, if we have a classifier that gives a label to the picture that we are generating, then we can direct the diffusion process in some way that the image that we are generating does not come from a random point in the space of all possible images, but we can direct the diffusion process towards the subspace where the pictures that we are interested in lie. How can we do that? Okay, let's recall the bias theorem. So the probability of a picture given a label is the probability of the label given the picture times the probability of the picture divided by some normalizing factor that we do not really care about. So if we have something that gives a probability of a label given the picture, and then something that gives the probability of the picture, we are done. So what gives the probability of the picture? The backward diffusion process. It reconstructs the probability distribution over the picture space. What gives the probability of a label given the picture? That's a classifier. So if we have both a classifier and a diffusion model to create unlabeled images, then we have glide. So basically we have DALL-E, right? Okay, this is cool, but this is also difficult to manage from an engineering point of view. Google said, why do you need a classifier in the first place? This paper actually was written with the idea in mind of investigating the performance of classifier-guided diffusion. During that process, engineers from Google understood that they didn't need a classifier. And so they thought, okay, maybe classifier-free guidance is a better title, and they renamed the paper. Classifier-free guidance means that you just train a diffusion model with not just the iteration as an input and the random noise, but you train the diffusion model with the prompt as well. And you directly estimate what was on the left-hand side of the bias theorem before. So what is really necessary to do this is to have a latent space where both text and image are together. But that's what Clip does. So you have all the building blocks kindly provided by OpenAI, and you can build a diffusion model guided by a textual prompt. There you have it. That's basically Midjourney or DALL-E. You need nothing more than clever engineering and lots of money. And there it is. So this is a picture from the paper of the first Stable Diffusion. We can see all the elements that we have discussed before. So we can see the original picture, encoding, latent space, forward diffusion process, right? Okay. Now, random noise in the latent space, backward diffusion, but come on, in 2017, someone said attention is all you need. So you don't need to use convolution in the UNet, you use transformers. So that's a UNet just with transformers, right? And then, we'll skip this. We have the decoder part and the output picture. You need to guide this diffusion model so you have text. But I mean, if everything is in the same space, you can also provide part of the picture. You can also provide let's say, a low-level representation of what should be in the picture, and so on. And you can give it to the model right here. Okay, this denoising step is used to increase the resolution of the picture and to make it better looking. I mean, that's the module that really increases the quality of the picture created by Midjourney or DALL-E. Very good. There it is. That's the end of the engineering part. I would like to close by discussing some limitations and merits of this technology. So let's start from the merits. This is a picture from the end of 2022. This is a very well-known Italian company that has created a campaign completely based on pictures generated by Midjourney. Of course, the campaign was pretty famous. Not everyone liked it. Fine. We can express opinions. But still, it's pretty clear that more and more companies are using these models in order to create their communication strategy, their communication assets. Why? Because you can create everything you want without designers, without spending time and resources into stages and so on, actors and so on. Very nice. But not always the quality of the picture we generate is good enough. This is from DALL-E. This is from the DALL-E paper by OpenAI. And we can see that these pictures are not really aligned with what the prompt is saying. But here OpenAI said, okay, we're cool. We invested tens of billions, most likely, to create the best large language model in the world. We can use it. Why should we take as an input of our diffusion model the prompt that the user gives us? Let's try to improve it automatically. Let's use ChatGPT to automatically write a better prompt that is a more detailed one. Why? Because details are very useful in order to guide the backward diffusion process towards the right subspace. So we take a prompt, we improve it, and then we give it to DALL-E to generate the picture. Smart. But from the same OpenAI paper, there are some issues in our model. At least OpenAI was, probably still is, but was very open in expressing the limitations of their model. When they published Codex, they told, look, it can give very bad results if you condition it on poor code as a context, and that's true. And for DALL-E, they told, look, it's not capable of writing text in the picture. Why? We don't know, actually, but we think that it's because we encode the prompt. So in order to have prompt and pictures in the same space, you have to encode prompts and pictures as vectors. If you want to encode prompts and pictures as vectors, how can you explain a model what a letter is? The atoms of your communications are token, no longer letters. So how can you spell a word to the model? You just can't. The model does not know what A or B means. That's the problem. And in Midjourney 6, this problem was almost completely solved. The point is that I don't know how they did it. And second issue, if we are automatically generating the prompts, we may have the same problems that ChatGPT has in the open. So it can hallucinate. So it can add details that were not there in the original prompt, and so the image that we produce can be misaligned with what we meant. That being said, as a final remark, this was a campaign promoted by Fever in many cities of the United States. Fever is a very famous website in the US to get professional services. And they said, okay, everyone is worried about AI coming from their jobs. Okay, she's a copywriter. AI took my job to the next level. So do not worry about AI, but learn to use it and learn to have it increase your productivity. This is it. I'm Emanuele Fabbiani, head of AI at Xtream, and this was a brief introduction about diffusion models. Before questions, a couple of technical remarks. First one is, we really like to contribute to conferences and meetups and to deliver public talks. So Luca is usually doing that with Python Milano and PyData Milan. Fabio is going to have a lightning talk in a few minutes. So please give me feedback about this talk, if you liked it or if you didn't like it, if you understood everything or nothing. Let me know, because that's the only way that I have to improve my content. Second, if you know about Xtream, there's something weird in these slides. I didn't use our usual colors and our usual graphics. That's because we are going to launch a new brand about AI services soon, and this is already the new visual identity of the new brand. So let me know what you think about that as well. You're going to be my beta testers for today. Oh, sorry, final remark, otherwise my boss is going to be mad. We are hiring. So if you're interested in jobs in AI engineering or data science, let me know. Fabio, I know you have some interest in that.
Okay, Lele, thank you very much for the talk. So I think we can open up the round of open QA. Don't be shy. Okay, there you go. Let's a big applause for the first question. Come on, guys. Oh!
Thanks for the talk. I'm not really super knowledgeable about this topic, so it was super interesting. Just wanted to ask you about towards the end where you talked about how, because you encode all the images, so there's usually a problem, for example, with the text and stuff like that. Just recently saw how, for example, Midjourney released where you can like fix personas of an originally generated image and let's say fix the face or the hairstyle or something like that, and then recreate other images from those. I know that they don't disclose any of these stuff, but would your guess be something along the lines of how they fixed it with the text? Because again, how intuitively how I see it is that if you encode it in tokens, that's going to cause problems, right? Because how would they freaking know that that's the face that they want to keep and stuff like that? And now they made it simply available by adding an argument that keep that face. So what would be your educated guess on this technology?
So the correct answer is I don't know, because as long as they don't publish their research in papers, it's really hard to tell. I mean, Hugging Face in this aspect is taking a different approach, and we all appreciate that. But if I had to take an educated guess, I would say, look, all modern diffusion models do not work at just one resolution. There is not just one diffusion process. There are many that work at different resolution and different scales between the original pictures and the latent space. So you have one diffusion model, very low level, another one in the middle, another one at high level. And you can condition at every level. So if you want to keep the face, you can build the picture at low level, that is at the semantic level. Then I don't know where, I have no idea, in one of the other diffusion processes, condition on the face that you want to keep. And this is telling, look, you already built a person doing something. Okay, now condition on this face, and you steer the diffusion process towards that specific space. So if I had to guess how they did it, I would say this is probably the solution, but I can't be sure. And for text as well. For text, I mean, all models were capable of building some kind of text, it was just wrong because there was no way of explaining them how our semantic works and how our lexicon works. But if you can make some kind of text and then you can condition at high level on our alphabet, then you can probably get a much better text in your picture.
Thanks a lot.
Yeah.
Just as a reminder, lightning talks after lunch, so sign up.
Come on, let's make a round of applause to Luca and to all the other volunteers that made this conference possible.
Who gets the second question? There are quite. Oh, die, let's go. Record number of questions to him, by the way.
So, just a quick question. I noticed you didn't use the word control net anywhere in the presentation. I was just asking if you could briefly control net.
Okay.
If you can put this concept or this family of models inside your presentation arc.
I don't know about them, so no,
okay.
I'm sorry.
Okay. Sorry.
There you go.
Awesome talk. May I ask how you guys are implementing, how to say, what kind of work you guys do with those, with the technologies in the image space? What is the kind of engineering that you guys do?
So, of course, we don't build Midjourney because we don't have either the knowledge or the resources to do that. What we do is to try and find applications of this technology. So what you really want to do is either use available services to integrate them into your product and let this image generation become a feature of your product, or use directly image generation on your own infrastructure. And even with Hacking Face, hosting and using these models is not super easy. So we come in and try to optimize the delivery of these services on on-premise infrastructure. So in the first part, what we do is actually doing a little bit of digital product creation. And in the other side, we're doing AI engineering. So what we're not going to do, and what I guess it's very difficult to do unless you're Microsoft or Google, is to build this beast from scratch.
All right, thank you.
Yeah.
Thank you for the question. Some more questions from the crowd? Was it so good? Ah, ok, va bene, Gabri. Okay.
I guess I'm curious about your opinion on the main application of diffusion models. Why do you think it's pictures, and what else could it be? You know, the starting point was thermodynamics. Why can't we just do forecasting with the diffusion models? With the diffusion model, I don't know. I would have to think about it, but I would love to hear your opinion.
Okay, these models are generative in nature. So the two things that you really want to generate are text and pictures and videos. Oh, by the way, Sora is a diffusion model. So Sora, the latest video generation tool by OpenAI, is a diffusion model with lots of clever engineering because videos are much harder than pictures to generate. But I think that the main reason why I see pictures here is because it's the use case that makes most sense from a business perspective. So from a scientific perspective, this comes from physics, and probably there are lots of application in physics as well. But that's your field, not mine. So I will not talk about that. For the rest, I don't think forecasting can be a use case. For forecasting, you want to use probably architectures that are closer to GPT than to this kind of models. Because what you want to do is to understand the future from a context. And that's exactly what GPT does very well. So I don't see really, in the industry, I do not see other groundbreaking applications outside pictures and videos. In science, God knows. Diffusion processes are used, for example, in derivatives pricing. They are used in physics as well. So probably
Neuroscience also.
Neuroscience as well. Great. So probably the next applications we're going to see outside creativity will come from academia and not from the industry, because there is much more interest there. Pictures and videos are used by every company. There is a huge market there, so that's why the papers about this stuff came out from OpenAI and Google, and not from, MIT and Stanford.
Makes sense. It's always about the money.
Always.
Che compagno. Okay, we have time for one last question. Don't be shy. Also, don't be behind the TV so I can't see you. But I have one, Ben. Can you say something about the state of video generation and synthesis? So what are the challenges? Is it just scaling because you need to generate multiple frames per second, or condition images on the image before? I know the looks.
So to start, I would say that I have no idea where to find data to generate videos, right? And
for context, Sora was released, Sora generates video. The CTO of OpenAI, Mira Murati, was asked by a Washington Post reporter, New York Times reporter, about where they got the data to train the model on, and she said she had no idea. Okay, this is about licensing, of course, and this was more like about shielding herself from critics, but it was fun. Okay, sorry.
Yeah, jokes apart. Generating videos is much harder. Why? Because a video is just a succession of frames, so you don't have to just generate one picture, you have to generate multiples, ideally like 60 per second, and you need to keep consistency from one picture to the other. So OpenAI and Runway and so on were already very capable of generating like a few frames, a few high-quality frames, and then concatenating them together to create short videos. But what, the point where Sora is really groundbreaking is that it can generate up to 1 minute of video while mostly keeping consistency. So if you check the first examples of Sora, you see this problem very clearly. So you see, for example, a car that is passing through a street that is gray in the first 10 seconds, and then it becomes yellow. Why? Because it's very hard to keep consistency between frames. So my point is we already have the technology there. The theory is this one. There is nothing more, probably. We don't have the engineering. Because, another retarded question. Why did OpenAI publish videos from Sora but not Sora itself? Is it worried about misuse in the election? I don't think so. I think they don't have the engineering to scale it up. If they have just internal customers, they can do something. If they have 200 million customers, as ChatGPT has, probably they don't have any way to scale the infrastructure up in an effective and efficient manner. So I think that the state of the art of video generation is we have the theory, probably most of it. We do not have the engineering yet. It's just a matter of time because, again, it's a huge market. The investments are in the order of billions of dollars per year. So sooner or later, someone will figure out how to squeeze the diffusion process so much that it becomes so efficient that you can generate lots of frames in very little time.
Thank you. One last, very quick last question.
Do you think about video generation that tools like DraGun can have the foundations for this kind of directions? I don't know.
So I'm not an expert in the field, but I think that GANs in general are a little bit outdated now because they have some inherent issues in training that makes diffusion models much easier to steer and to scale up. So for example, what GANs do is adversarial training, right? So with adversarial training, if you can fool your adversary once and it does not understand how to recover, then you can fool it every time with the same technique. With diffusion models, this does not happen. They have other issues, but this does not happen. And also the training process itself, from an engineering perspective, is less efficient. And these stuff work if they are trained on huge data sets for lots of time. So even small improvements in efficiency can make a huge difference because of the scale of the problem. So if I had to bet, again, that's just speculation. Don't take my word for granted. I will just say that I wasn't here if in a 6 months time GAN becomes state of the art. There is the recording, but we can make it disappear. It's Italy. So I would guess that the next big thing in image or video generation will be some kind of evolution of diffusion models, not really other kinds of architecture. What is really interesting in terms of different architecture, though, is the approach taken by Gemini, for example, where you train a single model on videos, pictures, text, all together, and you try to skip as much as possible the different modules, like GPT-4 as a module for text, a module for images, and they communicate. Gemini, for what they published, looks like a unique model where different data from different modality come in and data from different modality come out. So probably in a few years' time, or few months' time, it depends on the pace of innovation, we will have those kinds of models generating videos and images as well. So probably we are going towards even bigger and more expensive models that are truly multimodal. So not different modules for each type of data, but a unique model that can understand from different types of data. Also because, again, if I have to think about money, and I'm Google, I own YouTube. So all the web has already been scraped. I'm not sure, but I hope that they didn't already scrape the whole of YouTube yet. So what I would do is to harness the data that it's mine and train the next generation of Gemini on YouTube, given that they didn't already.
Grazie Lele.